Okay, good to go. So sorry for the delay. I was trying to figure out all the parts of this lecture and what's going on. Okay, just a quick reminder, as usual. What we were doing last time was the following. We were discussing how we process interrupts, right? And we did quite well. I mean, we talked about how we process, we talked about the general interrupt processing path, but what we covered was the processing of an interrupt when the privilege change is not required, right? And it was relatively simple, right? Just let me just remind you. Let me just remind you what was happening, right? So essentially, imagine you were running somewhere in a kernel, right? Those were instruction. Instruction pointer was pointing here. Suddenly, you know, maybe it's an external interrupt from a device, like from, for example, from a network interface came in, right? And you said, okay, look, the hardware. This is annoying. The hardware essentially said, okay, the hardware said, like, or maybe like for simplicity, maybe a timer interrupt arrived, right? That's what we were talking about. And when timer interrupt arrives, what you want to do is you want to process it, right? And you want to maybe switch from one process to another or something like that. And so what happened is that, imagine if you had a stack, right? The hardware pushed on a stack. Imagine this was your ESP pointer. The hardware pushed just a couple of fields on the stack, and one of them was this old instruction pointer, old value of the code segment, right? And some interrupts were pushing error code, right? And essentially, hardware said, okay, like I will use a specific table, which is called interrupt descriptor table. I will use the number of the interrupt, and for the timer, it was interrupt number 32. I will locate an entry here, and essentially this will contain a pointer to the interrupt handling routine, right? And we don't yet know what's inside this routine. We just agreed that it's almost the same. It's just a little bit of assembly and then regular C code, right? And we'll talk about it today. I will go through an example of an interrupt handling at the level of the source code. Then this handler, interrupt handler, runs for a little bit. Maybe it does context switch. Maybe it doesn't, maybe just decide not to do that. And at some point, this code invokes an IRET instruction. The hardware essentially looks up this stack and essentially says, okay, this was the instruction pointer before the interrupt. So I'll switch back to this exact location where you were executing right before the interrupt, right? So the whole idea of the interrupts is relatively straightforward, right? It just means that we're gonna preempt current execution and just execute something else. And of course, the operating system kernel might choose not to come back here, right? And we'll see, like when we did a context switch, we'll probably return from this interrupt, but we'll return somewhere else, right? And we will understand how it works. But for now, let's just imagine it's still relatively simple, right? And you say, look, the context switch is a good idea. It didn't happen though. And we will come back to the point where we're executing. Can you continue executing right here like nothing has happened, right? And that did not require change of the privilege level, right? And today we're going to discuss essentially the processing of the interrupt when a privilege level, when a change of a privilege level is required. So let me ask you a question. What are those privilege levels? I keep mentioning them, but can someone tell me what these are? At least what are the numbers? What do you know about privilege levels? At what level the kernel is running? Ring 3. User runs at ring 3. Ring 0. Okay, correct. So we know that the hardware has different privilege levels. Do you have an idea why? Why are those privilege levels? Why are they needed? Me ring -3, right, Dominic? You listen to that boot lecture carefully. Okay, why do we need privilege level? MMU. So that the user doesn't access a kernel memory, right? So at a high level, you're right, but this is a little bit harder to answer. At a high level, the idea is the following, that user code is executing inside a tightly controlled container. You can think of it as a virtual machine, although today we don't call this container a virtual machine, we call it a process, right? But essentially, user cannot escape, right? It cannot write memory of the kernel, can't do a read or write. It cannot also violate integrity of this container. So what do I mean by that? So for example, imagine user can reload the root pointer to the page table, kind of something like CR3. CR3 is pointing to the page table, right? And this is what you're working on right now in your homework, creating a new page table. And if user can suddenly affect CR3, this register, control register 3, then the whole layout of memory may change. It might prepare its own page table, right? Which might cover everything from user to kernel. Why not? User can do that, right? This attack would be possible. And this is why the update of a CR3 register is a privileged instruction. So at ring 3, user can only execute instructions which do not violate integrity of this container, right, of a process, right? And so instructions which update CR3 will result in exception. So they are not allowed. Only in ring 0, those instructions are actually allowed to be executed. So essentially updates to the CR3. Who can give me other examples of similar privileged instructions? We should know a couple by now. LGDT, right, update to the global descriptor table, root of the global descriptor table, right, which is updated with LGDT, load GDT. What else? Update to the interrupt descriptor table, right? Like the kernel should hide those page tables within the kernel part of the address space, so user cannot really like even move, like read or write them, right? And also like updates to the essentially GDT and IDT are not allowed. And of course, the user cannot actually switch back from ring 3 into ring 0 unless it goes and switches to a well-defined point in the kernel, right? And this is why we need this interrupt mechanism to make sure that the only way for user to switch from ring 3 to ring 0 is to land on this kernel entry point. And this kernel entry point will check the, for example, if it's a system call, it will check the input arguments, validate them, and then start executing the kernel, right? So this is important to understand, that those rings enforce integrity of the process, right? So essentially user cannot escape it. And the rules of those, like all the hardware rules are carefully designed in such a manner that it's like it's impossible to violate integrity of this boundary, right? Okay, let me quickly remind you, and this is what we were just talking about, but now more specifically, like I will ask you a question: can a process override kernel memory? Of course, the answer is no, right? You know that the answer is no. You just told me, right? So this is not allowed, right? And the question is like, why, right? So because the user is running at a specific privilege level, right? So every entry in the global descriptor table in the GDT, remember the table, each segment will have a privilege level. It's a 2-bit field, right? And it can range from 0 to 3. So kernel will be running at privilege level 0, user will be running at privilege level 3. And there are 2 levels in between, 1 and 2, which were used in the past, but right now they are not used in mainstream operating systems today, right? But essentially, and I will explain it in a second. So essentially, when we choose a code segment from a global descriptor table, the hardware will look at the entry in the GDT, will pick up this privilege level and will say, okay, look, whatever this field is, you will be running at this privilege level. Maybe it's 0, maybe it's 1, maybe it's 2, and maybe it's 3, right? And for user code, we will configure the entry for the user code segment in such a manner that it's always 3, right? However, and you probably are already tired about, you're tired from those explanations from the GDT, like you probably can hardly even remember what it is, right? But the idea, just to remind you quickly, is that the addresses which we're using in registers, move some error here, it consists of two parts. Remember this idea. So the first part is an offset, right, which sits immediately in register. And there is a second part, which is a data segment, right, which chooses the segment, and it chooses the entry in the GDT, right? And if, for example, this entry matches your privilege level, so for example, it's 3, and you're running currently at your current privilege level, or code privilege level is also 3, then you can go through this translation, right? You go and get the linear address within the segment, right? So you check the based and bounds checks, and then essentially you start translating through the page table, right? So at this point, the hardware may change this field. So essentially, may check this field, right? It says, okay, what is your current privilege level? Your privilege level is 0, for example. 0 can access all privilege levels, 0 itself, 1, 2, and 3 as well. But for example, level 1 can only access 1, 2, and 3, and so on. Essentially, like level 2 will be able to only access 2 and 3, and level 3 will only be able to access itself, level 3, right? So meaning that you cannot really, like, if you're trying to switch with a long jump, remember we did this long jump instruction where we put some code segment, right? And then put an address like start, right? Start 32, I think we jumped to start 32 when we were enabling global descriptor table and segmentation in general. We provided a code segment, which essentially was choosing a code segment with a privilege level 0. That's why when we were booting, we stayed at privilege level 0. If we would have jumped to privilege level 3, we wouldn't be able to invoke any of those privilege instructions. We wouldn't be able to essentially set up a page table, right? Because we wouldn't be able to load the CR3, control register 3, with the root of the page table, right? Okay, so the currently running code has a current privilege level, or the CPL value, right? So it was chosen from the GDT when you were jumping and using a new code segment register, right? So let me illustrate this idea. As I was talking before, like, we understand the point that 0 can access all privilege levels, 0, 1, 2, and 3. 1 can access only the privilege levels which have a equal or higher number, and so by definition 3 can only access 3, right? And as I was saying, some instructions are privileged, right? They can only be invoked at privilege level 0, right? So like loading global descriptor table, moving into a control register, into any of the control registers, the stuff like that, right? So let me illustrate you how this privilege level was evolving as we were booting the system. So when we started booting, we essentially started in a real mode of execution. Remember, it wasn't even like 16-bit mode of execution. It wasn't 32-bit mode of execution. It was only 16-bit mode of execution, right? So at that point, there was no privilege level yet. The code could access any physical memory, right? Of course, which was addressable by 16-bit instructions, right? At some point, we did this long jump, and I'm simplifying a little bit here. I'm putting 1. In practice, we put something like 1 shifted by 3 bits, right? But this 1 chose an entry in a global descriptor table, and this entry was configured with a descriptor privilege level of 0, right? We call this kernel code. And at this point, when we did this jump, we started running. So because this value was 0, right? We started running at privilege level 0. This is the reminder how we did it. So it was inside the assembly file in a boot.asm file, right? So those macros which we used here, they don't even provide us an option to configure a segment which has a different privilege level. You can't really like put a field which says 3 here. So we configure everything by default to run at privilege level 0 here, right? So this is what we've done during booting, right? So at this point, we're running at privilege level 0, right? Inside the kernel. And we'll continue running inside privilege level 0, right? So we essentially will configure, we'll boot into main, we configure everything, right? And that at some point, we said, okay, look, at some point, we will be exiting into user level code, right? We'll use an IRET instruction, Again, very similar to how we would exit from an interrupt without changing the privilege level. The hardware would put a code would pick up a code segment on a stack here. This entry will have number 4, for example. So we will pick entry number 4 from the global descriptor table, right? And this entry will have descriptor privilege level equals to 3, which means that there are two things here. First, where our current privilege level equals to 0, so we can actually invoke this IRET instruction, and the hardware will switch to the privilege level 3 because you can switch from 0 to 3. This transition will not be, you cannot invoke an IRET instruction being at privilege level 3 and choose an entry 1 in a global descriptor table, trying to switch from current privilege level to current privilege level 3 to privilege level 0, right? Because that would violate the integrity of this container, which I was just talking about, right? Why is that? Because you can return anywhere in a kernel, right? You could put any value of the instruction pointer here, which is like totally fine with hardware. The hardware just like whatever this value is, this is where you're going to be returning from the IRET, right? So transitions from lower privilege levels to higher privilege levels are allowed, but they're not allowed in a reverse direction, right? So, okay, so at this point, we will exit into the user and we'll start running at CPL 3, right? This is how we will eventually exit after we create the very first process. We're ready to run. We'll create this tiny stack and then invoke an IRET instruction and exit into the process. And we'll start running into, for example, a main function of the very first process, right? So is this idea of privilege levels clear to you now? Do you understand the thing that it's encoded by the segments, right, in a global descriptor table? And specifically when you jump between these various code segments, right, and there is only a limited numbers of ways you can change your code. You can change your code segment. So you can do an IRET instruction, you could do a long jump, right? Stuff like that, right? And you can always switch from a more privileged to a less privileged level, right? But not vice versa. The vice versa, I will explain how it works in 2 seconds. But is this clear? Okay, so this is how we were configuring our current privilege level. We're running into user, right? Privilege level 3. In a real world, as I was saying, only 2 privilege levels are used today, privilege level 0 and privilege level 3. And what's also interesting, all the segments which we use, they're kind of flat. It's called a flat segment model, which means that all the segments in the GDT have a base equals to 0 and a limit which allows access to the entire address space from 0 to all Fs, right? So roughly speaking, and I can tell you how we already looked at it, this is how x86 initializes its own global descriptor table, right? So essentially, remember, we covered these first 2 functions. So we looked at main. Then I said, okay, we'll detect other CPUs. We'll initialize this local advanced programmable interrupt controller, some magic related to interrupts. And here's the function which initializes the global descriptor table. If we look inside, remember I told you that on each CPU it will have its own global descriptor table. It's a great question to ask, why do we have a global descriptor table on every CPU instead of having one global descriptor table for the entire system? It will become clear a little bit later in the class, but I might ask it on the exam actually, right? And inside this per CPU data structure, there will be a global descriptor table, which contains only a handful of entries, not many, right? And inside this table, essentially, each entry is this segment descriptor, and we know what it is, right? It's a little bit confusing that, the base is spread across 3 different locations here, the limits spread across 2 different locations. The flags are also both here and here. There is also a type, right? Okay, doesn't matter. So you can use C code and essentially use those bit fields to essentially define this data structure. And again, when you're working on your homework, you do something similar. You define a segment descriptor just in assembly, right? And I mean, if you're very careful, you will see that the same fields are as actually defined, and you like put some magical hex values or binary values to make sure that some bits are zeros, some bits are ones, right? Okay. And if you notice the, like when we're going to be looking at the x86, we'll notice that the global descriptor table, as I was saying, is configured to have the basis equals to 0 and limits equals to the entire address space. And the question is, how do we really protect the kernel address space, right? So this is the real question. So imagine you're running in user, so somewhere in the addresses, which are somewhere over here next to 0, right? The question is, you do a move instruction or load or store, like a move instruction, which tries to access one of these addresses. At the level of global descriptor table, at the level of segments, the base is 0, so the address stays unchanged, right? And the limit is the entire address space. So you pass the check, actually. So you seem to be allowed to access this page, right? Because, like, remember I told you, you can restrict accesses with segmentation. You could have said, okay, maybe my segments end at the second gigabytes, for example, right? For the user, for these green segments, which are configured with privilege level 3. And maybe only the code segments will have, like, the ones which have privilege level 0 will cover the entire address space from 0 to 4 gigabytes, right? But this is not done because it's unnecessary. So who can tell me how, at what point these accesses actually get blocked? Why the user cannot access the kernel memory? Anyone? Do you remember this magical bit in a page table? It's user accessible bit. So essentially every entry in a page table, I then mark them green and yellow. So green are user accessible, and yellow, they access this yellow part of the address space, which is kernel, right? So each entry of the page table will have a bit here, and I have a slide about it, right? So both level 1 page table directory and level 2 page table will have a bit, right? If this bit is set, the coded privilege level 3 can go through this entry, which means that the translation will go through to the next level and eventually to the physical address. If, however, this bit is not set, only levels 0 to 1 and 2 can access or go through this translation, right? Which means only the privileged code running at rings 0, 1, and 2 can go through this entries in the page table. Let me show you the picture here. So user bit is set for those green entries, right? It will be set for those green entries as well, right? Right, in each of these ones. And it will not be set for the yellow entries, which means that even when you invoke the move instruction, which tries to access an address in a kernel range, right? And although this is allowed, the segmentation does not stop us here, right? Because segments start from address 0, go to the end of the address space. Both kernel segments, privilege level 0, and user segments, privilege level 3, they allow this address to be accessed. However, when you try to go and use this linear address as an input to the page table translation, it will go through one of those yellow entries here, and at this point you will get an exception. And at this point, the operating system will get in control and will terminate the process, right? Is this idea clear? Each entry in a page table will have this bit. It will be set for user for the pages which can be accessed from ring 3, will be unset for all other entries. And since it's only 1 bit, we have to somehow compress 4 privilege levels into 2 categories, right? So we split them, saying that privilege 1, 0, 1, and 2 can access, even though if the bit is not set, and the privilege level 3 cannot, right? If I remember, you said page table directory has user ring 3 for kernel pages, but the page table entry will have ring 0. Oh, hold on. What you were probably referring to is the fact that I said that X with 6 actually still has those entries as green. It sets these bits both here and here, right, allowing this translation to go through. So these bits are set. But at the second level of a page table, for the yellow pages, the bit will not be set, right? So you will go through the first one, but you will be stopped at the second one. That's what I was mentioning. Okay, is it clear now? So the pages are still protected, but the first translation will go through. I wouldn't do that this way, but they did it this way. Okay, so now we understand what privilege level are, right? We know what we like. User runs at ring 3, kernel runs at ring 0, right? And some instructions are privileged, they can only be executed at ring 0, right? Okay, so far so good. So now let's take a look at how the interrupt will be processed when we need a privilege level change. It's almost the same as before, but more security mechanisms have to be in place because we're transitioning from an untrusted user code to a trusted kernel code. And essentially the kernel cannot trust any values which it did not configure itself and which are not protected from the user, like meaning that the user cannot change them, right? Okay, assume we are running at privilege level 3. So assume we're running inside the user, right? So in general, each entry in the interrupt descriptor table will have a descriptor privilege level itself as well, right? And you might be a little bit confused at this point because you said, okay, look, you just told us that it only matters that what this privilege level is inside the GDT. Maybe it's 3 or maybe it's 0, right, for the kernel or for the user. Why do we have this privilege level inside the interrupt gate? The reason is to protect the interrupts themselves. So in a typical case, user code cannot invoke interrupt 13, causing a page fault, for example, right? Because that would be awkward. If you allow user to invoke this instruction, the kernel will get confused because user can like suddenly invoke a page fault, right? And so normally this privilege level is set to 0 to make sure that interrupt transitions are only allowed, right, when your privilege level is essentially lower than the one which is set in this DPL, right? But it only protects against invocation of this int3, right? Other interrupts, like for example, if you do a division by 0, will be still delivered by hardware, right? So they will not be stopped here. And asynchronous interrupts will also be delivered by hardware and will also go through, right? So it's only to protect essentially protect the user from the ability to invoke this int some number instruction, right? Okay, we got this. And the whole interrupt path looks something like this, right? So we're running inside the user process, right? So we're executing inside the user process somewhere over here, right? Or maybe, I don't know, like depending on how you want to. User has a stack, right? Imagine a timer interrupt again arrives. The hardware takes us through the interrupt table, right? Interrupt table, like before, it has 2 entries. One is a pointer to the handler. However, the second entry is becoming important now because the second entry can actually choose a different code segment, right? So look, this is the entry in the interrupt descriptor table, and you can choose a code segment entry over here, right? And when you're going through this transition, the CS will kind of loop you back, right? This code segment will kind of loop you back over here in the global descriptor table. And you can choose a different entry from a global descriptor table, right? Meaning that you can change from privilege level from CPL3. If this entry here chooses an entry which has a descriptor privilege level 0, you're switching from 3 to 0, right? And you will start executing this code at privilege level 0, right? Because normally user cannot change, but here you can. So the user cannot invoke a call instruction, right? Because the call instruction doesn't change a privilege level. So if you try to call here, like the same entry, the same address, for example, vector 32, you will get an exception. Why? Because this yellow page will be actually will not have the user accessible bit set, and means that you're trying to access a page which is only accessible by the kernel, right? If you're trying something like a long jump here, choosing an entry in the GDT which has a privilege level which is lower. So for example, you're currently at 3, you're trying to jump to 0. Again, this transition is not allowed, right? But the transition through an interrupt is allowed. Why is that? Because the kernel configures the entry point. The kernel says, okay, it's okay to switch to this privilege level 0, right? As long as you start execution at a specific address of this handler, right? And if it's a syscall, I will check all the arguments. If it's just an interrupt, interrupts don't have arguments, right? So you just have to ask the hardware what's going on, and the kernel will do that. But right, the user cannot really affect the execution of the kernel, right? Okay, so this is clear. So you transition from 3 to 0, start executing within a handler. Here is one interesting detail here. Can we continue executing on the same stack? So this is a user stack, right? Hold on. I'm trying to switch back. And PowerPoint doesn't have a good way of switching back. Okay, it switched back. So the question is the following. Can we continue on this stack? Who can tell me? Oh, goodness. I switched back and forth and will come on, like, why it doesn't let me? You should let me switch. So are you saying yes? Oh no, yes is Dominic from a previous question. So what will be the problem if you allow, okay, Surya, so tell us what's going on. Why can't you continue on the same stack?
It needs it because something might have happened. Like we need to clean the stack afterwards.
No, because remember why, and it's important for everyone to understand. The user level code can freely change ESP value, right? ESP can be set to some unmapped page. So maybe it's somewhere over here. You can say maybe it's address 0, but maybe address 0 is actually mapped, right? So, but let's pick an unmapped page. If the interrupt transition, like if the stack is pointing to an unmapped page, the hardware will try to push instruction pointer, code segment, arrow code on the stack, but this page is not present. So the hardware will enter recursively into another fold, which is a page fold, right? Saying, okay, there is no page which is not mapped. At this point, the page fold will not be processed, right? Because it's yet another interrupt. The hardware has to save something on the stack. At this point, it will result in a triple fold, and the hardware will reboot the machine. At this point, there is no essentially triple fold is this catastrophic condition under which there is no future progress, right? So essentially the only way is to reboot, right? So another attack which user can mount is even worse. User can put the stack pointing to some part of the kernel, and then the hardware will simply override those data structures with these values of the instruction pointer and arrow code and the code segment, right? And you can manipulate those addresses to make sure that you make up some meaningful values here, or you may even just wait for the kernel to like get some overwritten values and then just crush in some mysterious way, right? Is this clear? Because this user code can freely change the stack. The fact that you can like compile assembly instructions which just move into ESP, right? We've done it right before. Is it clear? Okay, we got this. So, which means that the operating system does not trust the value of the ESP register, right? Because user could manipulate it, right? Could have manipulated it, right? Okay, so what do we need to do? The kernel needs a fresh stack. It has to, the interrupt has to continue on this fresh stack, which is configured by the kernel, which is definitely mapped, and the hardware can save those several registers, which are immediately overwritten during the interrupt transition on this stack, right? One question, where can we get this stack from, right? The hardware has to learn, like, from somewhere, it has to learn where this stack is, right? And I can ask you a question like, what do you know about it? It's unlikely, right? So what's done is the following. There is task state segment. It's yet another data structure with a tons of fields, which are rarely used, most of them. The only two fields which are often used are the following. So there's a field which has a pointer to the stack, and a segment selector which chooses a data segment or a stack segment for the kernel, right? Because remember here, when you were running here at user level, your stack segment was pointing to an entry in the GDT, which probably had privilege level 3, right? Because, okay, you don't want to override the kernel data structure, so you through the stack, right? So although I don't think it would happen honestly, but it's an interesting exercise to change the data segment to 0 and let the user run with a data segment which is equal to 0, because if I understand correctly, the current privilege level will still stay 3, right? So I'm not exactly sure why this will introduce a problem, at least in this scenario, but maybe I'm wrong, right? But anyway, so essentially you choosing the stack segment, right, to match privilege level 0, and you're choosing the stack pointer from this task stack segment, right? And the hardware knows where this task stack segment is located, because there is like a special entry in the GDT which points to it, right? And the hardware uses this entry through a task register, right? So this is essentially the slide. So pointed by a special task register, TR, right, which is essentially picks an entry from the GDT, right? Okay, so we got it. So this way we can transition. So the stack is fresh, the hardware, like operating system, knows that the stack is mapped, hardware can push the data, save the registers on the stack, everything will be just fine, right? Okay, so what is happening here in more details? Nothing almost changes, right? So essentially what has changed is that we load the stack segment and a stack pointer from the TSS, right? And instead of just pushing 3 values on a stack, which we pushed before, it was code segment, E flags, and EAP, right? Since now the stack is also changing, right? We push these 2 additional arguments on the stack. Not we, I mean the hardware, right? So it chooses the old value of the stack segment and an old value of the stack pointer, right? Okay, but everything else is more or less the same, right? Then we eventually begin execution of a handler. So essentially, remember, we had this picture before. So if this kernel stack was empty, remember, before we were executing the interrupt transition, right? This is pointed by this entry in the TSS, right? Task state segment. Hardware will push the following things on the stack: stack segment, stack pointer, flags register, code segment, code pointer, and some interrupts will push error code, right? Okay, let me stop here for questions, if you have any. Good. This is compared to the stack uses without the privilege change. Essentially, we lost these 2 values, which were stack segment and ESP, right? So, but everything else is the same. So very similar paths, but as we understood, like on this kernel stack, so not on this stack, but on the kernel stack, the hardware saves those 5 things, right? Or 6 if there is an error, right? Okay, this is good. So we understand now. And if someone if you ever confused about how interrupts are delivered, this is a good picture. So essentially here you can say, look, I receive a timer interrupt. The hardware goes through the interrupt descriptor table, chooses the address of the handler, which has to start executing, chooses the entry in the global descriptor table, to switch from ring 3 to ring 0, right? And then uses the pointer to the TSS here to essentially pick a stack pointer and the stack segment, right? And save those 5 things on this new kernel stack. And remember, I told you that each process will have 2 stacks, one inside the user level, right? And one inside the kernel. So this kernel stack is allocated for this very reason. So you can process and interrupt while the specific process is running, right? Now you understand why we allocate 2 stacks, because one is not enough. Inside the kernel, you need to have yet another stack, right? Okay, so now we are ready to take a look at what is inside the interrupt descriptor table. And interrupt descriptor table has 256 entries, right? So the first 32 entries are reserved by the CPU vendor. In our case, it's Intel or whatever, AMD x86, right? Then there's a couple of entries which are device IRQs, also 32 entries. And then those guys, actually, I'm wrong, only 16, right? And then the rest of it is software configurable. So essentially, the operating system can either assign one of these to syscall to essentially use interrupt transition mechanism to invoke system calls in a very similar manner. We'll just take a look in a second. Or it can be assigned to some newer device drivers, and the device drivers, like for example, network cards, when they receive a bunch of packets here, they will raise a specific interrupt that will go to the network device driver, right? And let's take a look first at this first 16 interrupts, right? So this is, again, as I was saying, reserved by Intel. Those first entries are all synchronous interrupts, right? Not all, actually. NMI can be asynchronous, right? But typically, those are like division by 0, which is a synchronous interrupt, right? You're dividing something. Debug exception, right? So meaning that you have a special instruction XCC, which causes, like, essentially is a special instruction, which actually it's in 3, I believe. The debug exception is a hardware watch point, essentially. So in 3 instruction is XCC, I believe it's a breakpoint, software breakpoint, but it's a hardware watch point. So the hardware, you can configure hardware register to essentially react when you land on a specific address or access a specific address through like essentially load or store instruction, right? So, and so on. So like double fault is there. Your favorite page fault is here. Actually, it's not. 13 is general protection. I was wrong. So 14 is a page fault. There are various like alignment checks because some floating point operations have to be aligned. Remember, we aligned the stack for this very reason. Remember, we're aligning the stack to 16 bytes when we looked at real examples. And otherwise, you know, some floating point and vectorized instructions will cause an exception. Some catastrophic errors at the level of machine, kind of like, you know, maybe you have actually machine check is so rare that I don't even know the reason when it happens. So typically it's something like, I don't know, like the memory faulted completely. Like essentially you're trying to access a physical address and the memory controller returns some kind of an error. I can be wrong, so we should read a little bit about it. Right? So stuff like that. So this first 16 or first 32, which are reserved, and since I created this table, a couple of those were added here, but okay, I don't have them on the slide, right? But more or less clear. So if something, it's catastrophic conditions, and now you're debugging your homework, you often see something like first a page fault, then a double fault, and then a triple fault, right? Where's the triple fault here? Triple fault is not even delivered, so you only see the double fault. The triple fault means hardware already rebooted, right? Okay, so as I was saying, from 32 to 47 are IRQs, so essentially connected to well-known hardware devices like keyboard, timer, stuff like that. And then above it, you can actually, the software can configure it. And for example, Linux uses x80 for system call, or used to use it, right? Because now we have a faster way to transition from user mode to kernel mode with a sysenter instruction, right? And x86 will use x40, which is 64, right? So interrupt x40 is essentially a mechanism on x86 to invoke a system call, right? Okay, one important question. So you can actually, how do you disable interrupts? You can disable interrupts by setting a flag or a specific instruction flag. It's just a bit inside E flag register, right? Which is a little bit unusual, right? Because you say, look, is that really the way to disable interrupts? Which means, again, can a user code set this flag in the E flags register? No, it cannot, because otherwise the user code, which runs in some infinite loop, can set this flag and can run forever in an infinite loop. The operating system will never get the timer interrupt delivered and will never switch to a new process, right? So this interrupt flag is also protected, right? It's part of the security boundary, which ensures the integrity of the container, which is called a process, right, today, essentially to make sure that the process cannot like take over the machine by disabling interrupts and running forever, right? So it's important to understand. So there's a couple of exceptions, like, so first of all, logically, synchronous interrupts cannot be disabled, because if you're dividing by 0, right, you do a division by 0, you say, well, hold on, like, it's like, what does it mean to disable an interrupt here? Like executing next instruction, like it's undefined at this point, right? The outcome of this computation is not well defined. So of course, it doesn't make, or like you accessing memory and you accessing an address which is not mapped by the page table, right? Again, there is no real way to move forward from this. You need to stop, right? So in instructions like int something, int ox40, for example, a system call cannot be masked either, so it cannot be disabled. And so essentially what it means is that E flags controls, disables interrupts from external devices, like from a timer, keyboard, network adapter, disk, stuff like that, right? However, there's one special interrupt which can also be asynchronous, and it's called a non-maskable interrupt. So it's interrupt number 2 in the interrupt descriptor table. And this non-maskable interrupt is typically used for a very like the most critical conditions. So it's not even the device conditions, but some kind of low-level conditions which require immediate attention of the operating system. And those non-maskable interrupts cannot be disabled either, right? That's why they're called non-maskable. But the rest of it can be actually disabled, right? Okay. Let me quickly stop here and stop again for questions. All good, we understand how interrupts can be disabled. Okay, excellent. So now it's time, we understand the general interrupt mechanisms, and now our goal is to start looking at x86 source code to understand how x86 implement interrupts, right? Or interrupt handlers. And why is it so important for you? Because there will be a homework, and this new homework will ask you to implement a new system call, or maybe a new interrupt handler. We'll decide in a second, right? But essentially you need to know essentially how to deal with the code in such a way that you can handle interrupts, right? Okay, so one more function from the main.c. This one initializes the interrupt descriptor table. It's called TV init, right? So again, I have this call stack here. So it's code directory for main, right? And essentially what it does, it says, okay, look, I have a bunch of entries, right? Inside the interrupt descriptor table. And I have a macro set gate, which allows you to essentially like, remember this, the entries in the IDT, they're similar to the entries in the GDT. They're all like kind of like tangled together in some most unpredictable way. So it's impossible to set them by hand, but this macro is convenient, right? And so what this macro is doing, it says, okay, I will essentially set everything with the privilege of kernel code. Essentially, only the code at privilege range 0 can invoke int x instruction, right? Meaning that we forbid user from invoking those instructions at user level, right? And I will provide a vector, so I have a table of vectors, and I will provide a pointer, so ith element of the vector, right? And that's it. So essentially for all entries starting from 0 to 256, I will essentially fill them with those vectors which operating system created. However, one entry in this table will be special. Instead of providing 0, this entry will have 1 here. Why is that? Because we want to enable the entry, which is t-syscall entry, which is x40 on x with 6, right? We want to allow the user to invoke this instruction in 40 to essentially triggering a system call transition. That's why this one is configured with 1. This is essentially allows you to say, look, oh no, hold on, it's not the one, it's this descriptor privilege level equals to user, and for all other entries it's equals to 0, right? And this 0 and 1, this actually means disable future interrupts and this 1 means do not disable future interrupts. So it's also a little bit unusual. The delivery of the first interrupt by default doesn't always have to disable subsequent interrupts, right? And this is configured in an interrupt descriptor table. So essentially, if you put 1 here, I mean, it's some flag, right? So it means that the transition through this interrupt table transition does not disable subsequent interrupts. And it totally makes sense for the syscall because we want to treat syscalls as function calls, right? Normally function calls do not disable interrupts. So it's very similar here. You say, look, like just go forward, transition into the kernel, start executing the interrupt handler, but do not stop delivery of future interrupts, right? Okay, so it's called essentially a trap, right? So as I was saying, like we configure all the interrupts with privilege level 0, so the user cannot invoke them, and we can like only one of them is configured with privilege level 3 to make sure that only the user can invoke only one entry, which is t-syscall, t_syscall, right? Okay, and this 0 and 1. Syscall is a trap. Trap is a special name in Intel's literature to essentially name the interrupt which does not disable future interrupts, right? Okay, so now how does the interrupt code looks through the kernel? Like what really happens? Remember, I told you that we land on this entry in the kernel. Like, what do you think should be inside this vector 32? What will be the first couple of instructions which you would put there?
Validate documents.
You would do what?
Look at what type of interrupt is it. Like if it's an syscall, we need to know what type of syscall it is.
Okay, what type of interrupt, right? So, or interrupt number. Okay. What else? Any other ideas?
Validate the arguments if according to that.
Validate args. That's a good idea too. What else? You're actually missing the very first thing which you have to do.
I mean, push the old stack pointer or something like that.
No, but old stack pointer is already pushed by the hardware here.
Okay.
But what is not saved by the hardware? Look at this. We only save 5 things.
The current state of the running process, like all the registers of the process.
Exactly. So the very first we need to do is save general registers, right? Because even executing instructions might change those general registers, right? So we have to be very, very careful. We just have to execute the first instructions in such a manner that they don't change general registers, right? So let's take a look at how it works. So the very first things for the interrupts which don't push the error code, we'll just push 0 on a stack to make sure that the stack layout for the interrupts which already have the error code, it will be there on a stack, right? For the and like there will be this 5 entries which will push, which the hardware push, like stack segment, ESP, and so on, right? But for the interrupts which don't push the error code, we just push 0 here, just to make sure that, you know, after that, all the offsets like into those other fields are the same between the two interrupt paths, right? So we push 0 for vector 32 because the hardware does not push an error code for the vector 32, right? Then we push the interrupt number. So how do we know which interrupt was delivered? We don't know. That's why each entry in the interrupt descriptor table is unique, right? That's for the vector one, we'll push 1 here, right? We'll first push the error 0, and then we'll push 1. So later on, when you go deep into the kernel, you can come back to this value on the stack and see which interrupt was actually delivered. Was it the page fault? Was it a syscall? What the number, right? So we push the number. And these two instructions, they don't change general registers, right? They only check the stack. They only change the stack. The old stack pointer is already saved by the hardware, and we're on a new fresh stack, which is like configured by the operating system, right? At this point, we can jump to a new label, which is called all traps, because at this point, each entry in the interrupt descriptor table is unique. It just saves the number of the interrupt. After that, you can jump to one unified entry and start doing the same. On each interrupt pass, you will do the same things. But as you were saying, and this is the stack now, so this is saved by the hardware, and this is saved by the vector 32, the 0 and this 32 number, right? I will keep track of it. And this is your invocation stack, right? So it's hardware in 32, and the very first function which you landed in a kernel on was vector 32, right? I just to make sure that we keep track of what's going on. So inside all traps, as you were saying, we have to save all general registers. So we stop, it's called start building a trap frame. It's a data structure which will live on a stack, and it has a name, trap frame. We'll see how we can access it later. But essentially what we're doing here, we're pushing all the segment registers, right? Because maybe they will be overwritten later. And this instruction push all actually is a special assembly instruction, which is equivalent to essentially kind of like save a temporary ESP and then push EAX, ECX, EDX, EVX, push the temporary ESP on the stack, EBP, ESI, EDI, with a single assembly instruction. Of course, it unfolds into some microcode on the CPU, I believe, right? So it's this push all instruction, right? So the stack will now look like this, which is saved inside the all traps handler. So there's 4 segment registers and all general registers. I folded it into one entry, but really it's like whatever, how many 8 general registers which we're saving here, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Correct? Agree with this? So and if this whole data structure will be called a trap frame, right? Actually, there might be a mistake, maybe all by one, but maybe like this is the trap frame on a stack, right? So, and what are we doing next inside this assembly instruction? This is currently essentially what you're doing here. You're configuring the data and ES segments, right? So essentially you're saying, okay, I will be using kernel data entry in the GDT for data instructions. So the stack segment was already configured. That's why all these instructions which are stack related, they use this stack segment. So that was fine. But all your move instructions you will have to use the code segment, right? That's why you essentially, or not the code, sorry, data segment. That's why you reloading the DS and ES with this new values of the kernel data segment, right? Entry in the GDT. And these lines are no longer present in x86 because they changed the implementation of per CPU data structures. So, but essentially what was happening before, and I should update the slide, they were using a special per CPU segment to implement per CPU data structures, very similar to how Linux was doing it, or how we are using thread local data structures on Linux. Remember, on Linux, we can use FS or GS segments to essentially to keep track of where thread local copies of data structures are allocated, right? So, but x86 simplified its code a little bit, and this is no longer done, right? After that, you push the pointer to the trap frame on the stack itself, right? So what are we doing here? The idea is following, right? We're calling the trap function. right? The trap function is a function which takes one argument, a pointer to the trap frame. We know the calling convention. We know that if we want to invoke a function which takes a pointer, oh, that was cool. Wow. I didn't do this actually. I don't press the button. That's unusual. Oh, PowerPoint fails me today miserably. Got better now, sorry. Yeah, let me erase everything on this slide. So what I was doing here is, remember, this is a trap function which takes a pointer trap frame as argument, right? In order to preserve the calling convention, we have to push the pointer to the trap frame on the stack itself, right? Do you understand this idea? Which means that we save a bunch of registers on a stack, and this bunch of registers in C, we will refer to it as a struct, and this struct has the exactly same layout, so it has the same fields as the ones we saved on a stack, and this struct is called the trap frame. Now we essentially push the pointer to this data structure, right? Because this is where this data structure is located on the stack, onto the stack itself, so we can pass it inside the trap, which is a C function, right? And how do we push this pointer? It's the pointer itself is a current value of the ESP register, so we push ESP itself on a stack, right? Is this idea clear? Yes or no? Yeah, yeah. It's not yes, it's just yeah. Okay, got it. Almost there. Okay, okay, cool. And now we're inside the C function, right? So we say, look, show, like this is the code. Inside the C function, remember, we push the interrupt number on the stack. So this trap number is the number of the interrupts. So it's 32 in our case. And so inside this trap function, there is a giant switch case, which is okay, if it's a timer, which is like timer IRQ is 0 and or whatever, like it equals to 32, right? You say, okay, cool, we will do something, we will increment the number of ticks, and later on we'll actually switch to the process, which essentially here we say, if we have a process currently and this process is in a running state, the trap number is the 32, essentially a timer interrupt, we will yield the CPU. This is how we will end executing a context switch, and we will spend some significant amount of time on learning how this context switch works. So we'll come back to it later. But essentially what we've done, just the idea, like this is how we entered the kernel. So essentially with assembly instructions, we constructed a specific layout on the stack, right? And this layout matches the layout of this stack trap frame data structure, right? And now we essentially can address any register which got saved, like with this trap frame, for example, EAX will have a pointer on this, like to the register which the program had when the interrupt arrived, right? So essentially this is what we've done. Okay, and essentially we exit from the interrupt in a very similar manner. So when this trap function returns, right, it returns, since remember, we called the trap from this location. Of course, it returns to the next instruction after the trap, right? Because this is how the call instruction works. We essentially say, okay, forget this ESP value on the stack, just add 4 to it, right? And again, which means that now the trap frame is at the very top of the stack. So we'll we'll start doing essentially the same business as before. We will pop all, it's like push all instruction, and a pop all is a symmetrical instruction. It will restore all the general registers, like all 8 general registers. We'll just pop all the segment registers which we saved, GS, FS, ES, and DS, right? We'll add 8 because we saved trap number and error code in the stack, right? So we'll throw them away as well. And at this point, only these 5 values which were pushed by the hardware are needed for the execution of the IRET instruction. So at this point, the stack will be exactly containing only these 5 fields, right? Right, this is the value of the ESP here. And when we execute the IRET instruction, it will pick up the what is it, code segment and EAP value, and we'll essentially restore the code segment to privilege level 3 and the EAP to whatever the user value had when interrupt arrived, right? Is this clear? The return from the interrupt as well. Right? So it's symmetrical code, like same assembly, same symmetrical code. But essentially, that's kind of convenient. You say you entered, mostly you ran in C, you did all the kernel logic in C, and we will take a look at how we handle a system call, and then you exit with this sequence of assembly instructions and IRAT instruction at the very end. Okay, so how do we define this drop frame? So it's just a slide by slide. I go again like through the same explanations, but I already covered it, so we can skip, right? So, and again, like after all these transitions, like the kernel stack is empty again. We're running inside the user, right? This is the entire interrupt transition. If anyone again asks you a question, this is what you have to look up and say, okay, I understand how we enter in and how we exit from the interrupt. So now again, the second thing which is interesting to us is essentially invocation of system calls. It's just one specific interrupt. It's int x40, right? And you say, look, how do we process it? In a very similar manner how we process other interrupts. So as I was saying, like int n, since the kernel controls the location of the interrupt handler, it's secure because user can enter the kernel only through a well-defined entry point, right? So, okay, so how does it work? The same transition, now it's only syscall vector 64. So the same vector 64 instead of 32, you're now using 64. Again, you will choose the location of the vector 64 in the kernel code based on the entry in the interrupt descriptor table. Again, the same code segment, which will essentially transition from privilege level 3 into privilege level 0, right? We will similarly choose the kernel stack segment and kernel stack pointer, and the hardware will similarly save these 5 entries on the kernel stack, right? So again, the very same business, vector 64 will push error on this stack. We'll push like error to make sure that the stack has the same representation between the interrupts which push the error code and the ones which don't. Push number 64 on a stack because, okay, we have to distinguish it later. Jump to all traps, all the same business as we did before, right? So this is wrong. This I have to update the 64, right? Then we again do the same business of saving the registers, saving code general registers, reloading the data segment, pushing ESP as an argument to trap, going into the trap function. This is how the stack is laid out. So this is the trap frame. Oh, sorry, this is the trap frame data structure, right, on the stack. And however, inside the trap function, instead of like reacting to this switch, which picks the vector, which picks the timer interrupt entry, now there is an if statement which says, okay, if the trap number equals to t_syscall, user tries, it's a syscall interrupt, which means that user tries to invoke a syscall. We check if the process is killed. There is some specific logic for what to do when it's killed. We exit the process, right? Clean up all the resources. Otherwise, we set there is always a currently running process data structure. We update the trap frame to make sure that we have a reference to this process, we know where the trap frame is. And then we enter this syscall function, right? And again, this is the stack, invocation stack. So hardware invoked int 6, like what is this? Int OX40, right? Or 64 in decimal. Then vector 64, they're all traps, then this trap function in C. So we're now getting into the syscall. The user passes the syscall number inside the EAX register This is just a convention between the operating system and the user level libraries, right? So essentially we can distinguish which system call user tries to invoke. Maybe it's a sysread, maybe it's exec, maybe it's fork, right? And so all trap, which saved this trap number, I mean, it's not even all trap, it's like inside the vector 64, we push number 64, right, on a stack along with the error code, which was 0 in this case, right? And so we can access it. So essentially we can access it like this: process trap frame, because this is, remember, we updated the current process trap frame pointer, right? We read the syscall number from the EAX into this local variable num. And what we do next is essentially the operating system maintains a table of system calls as an array, right? And we're just saying, okay, well, elements of the array are function pointers. C allows you to like have function pointers as members of the array. So you say, well, pick a number, pick an element number n, number num, right? And invoke it. This means that invoke a function, and this function will return an error, right? Or maybe no error. And again, this calling convention for system calls is that the error will be inside the EAX register, right? Or return value. And that's okay, right? So let's take a look at what's going on within this table. This is how this table is initialized. This is how you initialize an array of function pointers. This is the C syntax for it. And each element of the array is initialized to a specific kernel function which handles a specific system call. So sysfork, sysexit, syswait, syspipe, read, kill, and so on, right? Again, the beauty of it is that all system calls fit on one page, right? And this is the real definition of the data structure, right? So x86 is really reasonably simple, right? And you essentially pick one of those system calls by providing an entry in the EAX register. Okay, so now the question is how we typically invoke system calls. After all, it will be a little bit weird to write something like push some arguments on a stack. So for example, you're invoking an exec system call, which takes a couple of arguments, like it takes a pointer to an argv array, sorry, pointer to the name of the to the string which encodes the name of the process, right? Stuff like that, right? And then invoking this int tsyscall. So it would be nice to have a more convenient interface for invocations of system calls, right? So, and what the user level libraries are doing, they have this user.h file, a header file, which provides definitions for each system call, right? Essentially, so exec takes 2 arguments. This is the name of the program. This is the path to the program, like, I don't know, init, for example, right? And this is the pointer to the array of arguments, right? So like exactly how we were doing it before, right? So user can actually invoke a normal function, right, at user level. So what do you think will be inside this function? Because in the end, inside this function, we will have to invoke int ox40, right? This is kind of clear, right? It's kind of inconvenient to do that every time you want to invoke a system call. So inside this function, why is this? Inside this function, we'll use the following assembly sequence. So essentially, there's another file here, which is called usys.s, right? And so we'll use this assembly macro to generate the following sequence. So for example, each syscall will have a name. So for example, if we use something like a read, which I'm using as a running example here, or exec, or fork, right? Then this macro will create a global label with the same name. So it will be like global fork, and here will be like something like fork here, right? And then it will be concatenated with a name, which means that it will push the number of a system call into the EAX register. And then it will just invoke the int ox40 instruction, right? So how does it work? Did you get this idea that usys.s has essentially a tiny assembly sequence which can invoke every system call in a system, right? From user level by generating essentially each of these macros will expand into an entry like this, right? And so, for example, if we want to invoke something like, I skipped this because I was confused about the ordering here. If we want to invoke something like a write system call, right? We write, this is what we write in our code, right? So it's a write, we pass something like a file descriptor, standard input, standard output as an argument, pointer to the buffer, we'll push size of the buffer. The compiler will, from this essentially header definition, the compiler knows that this is the function which you're trying to invoke. It takes 3 arguments, so it will push those arguments on a stack, right? So this is the file descriptor 1. This is the address of this buffer, which was probably defined as a global variable. And this is the size of the buffer, which is passed inside the EBX, which is currently inside the EBX register. Then it will call this label. This label for write will be generated by this assembly code, which I was just showing you, right? And what I wanted to show here is that if you look at these examples of assembly, you might see a slightly different example because different versions of the assembly generate different versions of the different versions of GCC generate slightly different versions of this assembly code. So don't get scared. So instead of those clean push instructions, which I just mentioned like a second ago, you might actually have a couple of moves, right? Which just essentially just move something on the stack, ESP plus 8, ESP plus 4, and here just into the ESP. So this is the file descriptor number 1, right? This is the same address of the buffer, and this is the size of the buffer, which is n, right? So again, but did you get the point? So essentially, you have a header file which provides you with the name of the label and the signature of a function. From that signature, the compiler can generate the call site invocation. Then it jumps to this label, and the label itself comes from this assembly macro inside usys.s. And this is how essentially system calls are invoked from user level, because here inside the syscall.s, you have this int instruction, which essentially drops you into the kernel, right? So, okay, so let me stop here. And next time, we're going to finish system calls. We are almost done. Essentially, the only thing which we haven't covered yet is how the system calls pass arguments, because what is the calling convention for the system calls, right? And how the kernel essentially validates those arguments. This is, remember, I asked you, what do you have to do inside the interrupt? So if it's a system call, you really have to validate all the arguments which are passed from the user. So we will do that next time. Again, right now, let me stop. I'll take any questions if there is anything unclear, and otherwise I will see you next week. But again, I'm ready to take questions.
Can we have 2 interrupts for the same process?
Can we have what?
2 like multiple interrupts for the same process, like multiple interrupts coming, like one hardware interrupt and like a syscall. Suppose the kernel is processing a syscall, can there be a timer interrupt for the same process?
Right, it can, because remember, and this is essentially what I said. So imagine you, and that's a very good question. So imagine you did something like, again, write system call, passing 1, buff, and n. Remember that this int OX40, when it goes through the interrupt descriptor table, the entry in the interrupt descriptor table is configured in such a manner that it does not disable subsequent interrupts, which means that we go through this vector 64, interrupts are still enabled, you push a couple, you push 0, push, sorry for my handwriting, push 64, you go to all traps and save all the registers, then you go to the trap function, start processing the system call, and at this point, maybe a timer interrupt is arriving, right? And interrupts is still enabled. So which means that you can actually, again, at this point, you're already executing at privilege level 0, right? Because you were here at privilege level 3. You transition to 0. So this is where you started as privilege level 0, right? Right? And now you're transitioning again through the interrupt descriptor table. Now you're taking the entry, let me change the color. You're taking entry number 32, right? 32 is actually configured to disable interrupts, right? But again, you will do the same, vector 32, same push, 0 for the error code, same push for the 32 number, same jump to all traps, and again, land on the trap function. And since here, when this interrupt came, you already were at privilege level 0, you're continuing on the same stack, right? So your kernel stack will look like there will be a trap frame for the first interrupt for the syscall, right? And then the nested interrupt, it's called nested, right, will be delivered. And again, at this point, you disable the interrupts because when you were transitioning, it's like all the non-maskable interrupt can be delivered at this point, right? But x86 doesn't handle non-maskable interrupts. So, and this is how it may work, right? Hopefully this answer helps.
Yeah, got it.
Okay. Yeah, so it can happen. It's called nested interrupts. So, but you can very well say, okay, I don't want to deal with nested interrupts. I can rather disable interrupts right here when I transition through a syscall. That's also done in many kernels. So sometimes some of them like disable interrupts at the moment they get in. And some of them actually keep interrupts enabled for almost all the time. So the timer interrupt will re-enable interrupts, and x86 will do that the same, like halfway through the interrupt pass. You will see when we'll get to context switch. Okay, good. Any other questions? Okay, then I'll see you next week, actually. Thank you so much. See you guys.